Hello, everybody, and welcome back to day 3 of the ICITC and ITU conference, focusing on radio spectrum for IMT 2020 and beyond. My name is Dan Kraft, and for those of you who have been here for the last 2 days, you'll know that I'm honored to be acting as your MC for the conference. As I said, I'm delighted to have you all back with us for the 3rd day of the event. It's actually hard to believe we're already 2 days down and are now at the last day of the event. Hopefully you've all been with us for the first 2 days and have been able to catch some of the fantastic, thought-provoking and forward-looking discussions that have been taking place. As a reminder, if you've missed anything that's happened so far, or if you wanted to catch up again on anything that you'd seen and wanted to watch again, then all of the presentations, all of the discussions are available to watch via our YouTube page. You should have received details and links for how to access this by email. Those were sent by email to you, I think, after the first day and again after yesterday's proceedings. But if not, if you haven't received those, or if you've got any questions at all, then please just get in touch with my colleagues using the chat area of the platform. Talking a little bit about the chat area, I wanted to say a massive thank you to all of you out there who've been using the chat area to post your comments and questions during all of the sessions at the event so far. We've really appreciated all the thoughts that have been coming across in that way. And we've, of course, been passing those on to the moderators at all the sessions. And it's really helped to provide that interactive and lively discussion in all of our sessions so far. So please do continue to post messages, continue to post your questions, your thoughts, your comments via that chat function. And we will be bringing those across to the speakers in each of the different sessions. And the chat area is not the only way you can make yourself heard today, because at the end of the day, we're going to be asking all of you out there to help us close the events and draw final conclusions. Because our final session for the day today is entitled Have Your Say. And as the title of that would suggest, it's your opportunity to come and actually have your say on what you think are your key takeaways for the conference. So you will have the opportunity to bring your audio and your video feed live, to come up onto the stage and to let us know what you think of the discussions that have taken place, to let us know what you've maybe got out of the event, any key conclusions, key takeaways, and we really do want to hear from you. So that's going to be the final session of the day today, so please do make sure you stick with us for that. And yeah, as I said, we want to hear from you. We encourage you to please come up onto the stage and give us your thoughts and make your voice heard. So now on to today's proceedings. I'm delighted to start today by introducing our next keynote speaker. We've been really honored to have heard already from a number of key thought leaders throughout the 2 days of the event so far. And we're now continuing that very welcome trend by welcoming Asha Keddy, Corporate Vice President at Intel Corporation, to deliver a keynote presentation. Now, unfortunately, Asha couldn't be with us in person today to speak, but she's very kindly recorded a video contribution just a couple of days ago, and we're going to be hearing that now. So over to the video. It's Asha Keddy, as I said, Corporate Vice President of Intel Corporation, and we're really looking forward to hearing what she has to say.
Thank you to CITC and the ITU. And I'm delighted to talk about how wireless technologies will transform commercial use cases, and both economically and from a societal point of view. Next slide, please. Now, if you look at the data trends that challenge our networks, billions of devices will become connected. And when you look at these billions of devices over the next few years, more data will be generated from devices. And this will drive the need for capacity. We don't even use a lot of the data that we have today. And now machines will be talking to each other on settings or parameters and all. The second big change is around video. More than 80% of the content will be video and visual in place. So you need things like buffering, and becomes a deal breaker. You need real-time systems, you need visual augmentation and all. So that's also a different trend that is actually looking at how we design our systems. And third, machine-to-machine communications will create all kinds of opportunities, especially around time synchronization, or the need for time synchronization, the need for reliability, as reliable as a wired connection, 99.9999%, and super low latencies, where things just happen like with 1 to 3 milliseconds or even less. So with these data trends, our network designs have to change. To put it in perspective, when networks were first designed, like in 2G, 3G and all, they were all designed for phone calls. And none of these that I'm talking about are talking about phones. It's an era that's around society, enterprises, industries, all way beyond the smartphone, towards creation of a fully mobile, intelligent network. Next slide, please. So if I look at the shifting data on the nature of how data is changing, as I mentioned before, the original calls were around phone calls and all. And then today, when we look at data, it's really not about inbound. It's really a lot more about inbound, not just outbound, and more unstructured, more uplink. If I'm at a concert, or if I'm uploading my homework or taking a class, a lot of it is what I'm uploading. TikTok, all these kind of things. We're creating content, with whether it's through YouTube or other means. And a lot of this content increasingly is latency sensitive. And also, we need to use it at the point of origin, which is, the more the data travels, the more expensive it becomes. So we also need a lot of data that is processed locally, especially like in industries or enterprises and all. The relevancy of the data also is contextual. For example, I'm speaking from Portland right now, and the traffic patterns and the weather patterns in Portland may not apply to where you are. And so there's no point taking a lot of this data beyond where it is. So, net, the shifting nature of data motivates a new generation of technologies that are increasingly mobile, increasingly distributed, and there's more kinds of processing that are happening both at the device level, at the places on-premise near the device, which is on-prem edge, the devices that are off-prem edge, or in the network, in the cloud, and everywhere in between. New formats, new thinking, new techniques, everything is starting to change. Next slide, please. So when we look at computing and comms paradigms and how they shift in each decade, you can see that the pendulum swings back and forth between centralized and distributed. In the PC era, before that, there was the mainframes where everything was centralized. In the PC era, we were able to have personal use of computer, where we could shrink compute and storage. And that was then we started storing things in servers. And then there was cloud, where you could then put your movies and have a lot more content. But now, with the explosion of content in the consumer world, we want that same kind of revolution in other areas, including how smart cities work or businesses work. Now we're getting it back from the cloud to a more distributed environment. And these resources are distributed and orchestrated all the way from the endpoint through the networks, through the cloud. Along this evolution and revolution, the ecosystem of 2G, 3G, and all also changed. 2G was about voice calling and data apps. When 3G started, there's an app for that. And in that, we used to have to connect to Wi-Fi. It wasn't IP-based and always connected. I still have one of the apps there's an app for that world when we had 3G. It's 100 push-ups because I haven't gotten quite to 100 push-ups yet. And then when we look at 4G, we went to an IP-based network. The killer app for 4G was actually video calling like FaceTime Anywhere was one of the original ads, I think, on the iPhone and all. But when we could be connected everywhere at every time, we had a consumer revolution with like the gig economy. We had so many industries that took advantage of being connected all the time. And today we can't even imagine life without it. I never thought that it would be the end of more taxi unions and Uber and Lyft and all. So net, technology can be predictable, but what people do with it is not. Um, and last but not the least, when we go to a more distributed world, the same kind of evolutions and revolutions that happened all the way from when it was something that we used to hold our cell phone and use it for emergencies and were expensive, and now it becomes a center of our personal universe, we'll have the same revolution towards much more in the industry and other areas. Next slide, please. To make all of these demands, the networks are very critical, and the network transformation is accelerating. 10 years ago, the network started moving from a fixed kind of environment to a more general purpose environment. It used to be that you'd have to have specially trained engineers and technicians who could then climb the pole, tilt the antenna, fix the things and all. And even rolling out device services like push to talk could take months. Now, with more general purpose and virtualized environments, it's much easier to roll out the services because it's done through software. And we have many environments, including open source environments, with checks and balances that even help with the security aspects of things. And so the traditional network, you had like extremely fixed points of compute, analytics, storage, and they would talk and connect and have things be centrally processed. Today, we have general purpose equipment and general purpose networks where things are completely distributed, and you have compute, data, storage embedded in every piece of the network. In addition, you have different latencies at each point. And as I mentioned, the nature of data is changing. The types of users are changing. And then we use these compute, analytics, and storage to do different functions throughout the network. For example, when it's latency sensitive and we need things right there, for example, if I'm walking through a factory and I want to look at augmented visuals of defects or some problems, I need low latencies and things are on-prem edge. If I'm, just waiting for like some pictures to get downloaded, a cloud network is okay, right? And so these end-to-end latencies and all also drive based on the quality of service that we need, different kinds of uses. Next slide, please. I'm going to talk both about 5G and Wi-Fi, as both are critical in this transformation. In 5G, Release 15 was a nod to LTE and the networks of the past. And Release 15 was really around continued mobile device evolution and evolution of, audio and video and use cases like that. And with Release 15, we also had we were able to have it backwards compatible to the LTE networks. And there were new concepts introduced, such as network slicing and initial support for URLCC, which is ultra reliable low latency support. 10 gigabits peak mobility and massive MIMO and more capacity kind of stuff. So this was very good, but only the beginning. Just like in any generation over the 10 years of that generation, you get more and more features, right? Remember LTE and LTE Advanced? Now, with Release 16, it starts becoming more revolutionary and not just evolutionary. There's a huge focus on enterprises and also mission critical applications. There's expanded low latency support that, along with precision things like time synchronization. This allows things and machines and different kind of things to be, whether it's through daisy chains or through other areas, right? OT time synchronization becomes important so that all the machines and all the devices are coordinated. The concept of the non-public networks or private networks became front and center, and support for these kind of networks where you can have enterprises go online became a big part of Release 16. And our unlicensed, which is unlicensed technologies or use of unlicensed bands by 3GPP, also took front and center stage, and continued evolutions like vehicle to everything also. Another one that continued the focus on enterprises, industries, and stadiums and all like that are things like indoor accuracy. Indoor accuracy initially is up to 3 meters, and this will be improved in Release 17. But it's the start, and it becomes very important when you start looking at things like AGVs or indoor positioning and all. Net, what you can see from these features, it's really about transforming the enterprises and businesses into something where they're fully connected and they can use the reliability of the wires with the bandwidth applications that are needed to get this work done. Release 17 continues a lot of this, and there's more work around machine type communications, including, how can I get more battery life? So this goes towards the low data, and how can I get battery life of 10 years and massive machine type communications. There's more bandwidth support, there's more features that are needed, and also, what we call reduced capacity devices, which are very simple devices like sensors and all, and how we currently look at mesh. There's also talk about how we even take this to the next level with what we call Release 18, which is in study phase. So if you take a step back and you look at how industrial IoT, smart manufacturing, smart cities, enterprises, and all are being evolved, and the next steps around agriculture, healthcare, and more. All these use cases need a lot of spectrum. Depending on the type of use cases, you need like large bands of spectrum, or you need small bands of spectrum, but that go the distance. Net. Nothing can be done without the use of a lot of spectrum. And 5G has got a lot more spectrum than in the past, and it still needs a lot more in the future to enable the vision of a fully connected, mobile, intelligent society. Next slide, please. Wi-Fi is also advancing with each generation. Wi-Fi used to be designed around peak performance and home use and enterprise use. Wi-Fi has already solved a lot of the problems around private networks, because when all of you have probably used Wi-Fi today already when you're listening to this. Wi-Fi 6 and Wi-Fi has taken a design turn where they've looked at the densification, or how do you increase capacity, not just speed throughput, and start adding features that don't exist. So they have much larger channels, up to 160 megahertz channels, and high QAM. And so that gives faster performance. And compared to its previous generations, the latency is also improved compared to Wi-Fi 5 by 75%. Wi-Fi 6 extensions, or Wi-Fi 6E, takes this to the 6 gigahertz bands and beyond. Wi-Fi 7, which is and Wi-Fi 6 will be launched next year, 2021, or in 2 weeks. Wi-Fi 7 essentially is targeted at 2024. A lot of it is still in progress, but in net, it'll have a 7.2x faster performance than Wi-Fi 5, with channels as high as 320 megahertz. So these are, it'll have more multi-link operation, better time, TSN support, and even lower latencies. And there's a lot of focus on improvement on worst case latencies, jitter, and all of these kind of stuff. All of these technologies also require a lot of spectrum. And Wi-Fi, because it is focused on unlicensed use and has already solved a lot of the ease of deployability, is only seen as getting stronger and stronger. And whether it's through offload, or whether it's through independent networks, or whether it's through things that go to the cloud, for information, for example, when you use Microsoft Teams or such devices at work. Next slide, please. So $4.3 trillion. That's what KPMG says that 5G will unlock. That's like the GDP of country number 5 or 6 on the globe. And if you start looking at how much money we're talking about in manufacturing or technology sectors, finance sectors, and professional services, it's a lot. It's like GDP countries number 21 or 22. And all of this is because of capability, reliability, efficiency, and the transformation. It is so important for us to be able to do a lot of these use cases, and much of it even involves leaving this place in a better place than we found it, right? For example, on healthcare, or improving safety on mining, or transport and all. So when I look at this, none of this can be done without the foundation, which is spectrum and different types of spectrum usages. Next slide, please. Wi-Fi economic value is again $3.5 trillion just by 2023. Again, think of it in terms of GDP. It's huge. It's symbiotic with 5G, as I mentioned before, and has the advantage of even being easily deployable in small networks. 60% of global mobile traffic by 2022 will be offloaded to Wi-Fi. So it plays a critical role in how we work this and integrate both Wi-Fi and 5G technologies. Next slide, please. So, net, to summarize, when I look at recommendations for best use cases of spectrum resources, Intel develops both Wi-Fi, Bluetooth and unlicensed technologies, and also licensed technologies like 4G, 5G products. And we want to ensure there's a suitable regulatory environment that pushes and promotes both kinds of devices, both kinds of network, and both kinds of use cases. Additional spectrum is needed in the very important bands for 3 to 5 gigahertz for 5G and those areas, and unlicensed technologies in the 6 to 7 gigahertz. It's quite important that we look at, making use and be able to take the radio and tune it. And these bands that I discussed already go naturally to where spectrum already exists for these technologies. And we've also seen that wide area licensed implementation has already been successfully implemented in the mid-band spectrum or the 3 to 5 gigahertz spectrum through provisions that protect incumbents. Unlicensed devices are better suited in general for supporting exclusion zones and limiting terrestrial stations to indoors. And in 6 to 7 gigahertz, we can do just that. Net, I would like to finish by saying thank you again to CITC and ITU on this super important, and for having me here on the super important topic on spectrum. And my main point is we need more spectrum, lots of it, in a way where we can use technology to figure out how to share with incumbents and other areas and work together towards a fully mobile, connected, intelligent society. Thank you.
Asha, thank you very much. And some very fascinating thoughts you've given us there, and an excellent way to kick off the discussions. And I'm sure we're going to be picking up on more of those issues in the sessions today. So we're going to move straight on to our first session today. The sessions are actually going to be split. The main panels we have are split into sessions looking at different frequency ranges. We're going to be looking at, later on, we're going to be looking at the mid-band and the high frequency ranges, but we're going to be starting off straight away now by looking at low spectrum bands, low frequency bands, so bands below 1 gigahertz. So the panel for that is going to be starting here in just around about a minute or so. So please, I do invite you to stay where you are. And it's going to be moderated by Uwe Beider from Roder and Schwarz. So Uwe will be with you very shortly to get started with the first session for the day. I will then be back after that to introduce the rest of the proceedings. So for now, a big thank you again to Asha. And as I said, stay where you are, and the next session will be starting in just around about 30 seconds. Thank you.